recording. Welcome to week 4 of MagMedX 2023. Today we have the pleasure to have our speaker, Dr. Mohammad Havaei, to give us a seminar on generative modeling. So we'll get started as soon as possible. Here we go. As I mentioned, the theme of this week, which is tomorrow's workshop, will be on transfer learning, medical imaging, and today is our seminar, and we have the pleasure to have Dr. Mohammad Havaei. Again, if you have questions, send us an email. We have had 3 weeks so far for MagMedX 2023, and we have also had 3 tutorials during the week, all on Thursdays, but they are really dependent on that mentor's schedule of that week. So we will announce the availability of this week's mentor as soon as possible. For you to make up any missing attendance, the mentors are making their quizzes, and you can watch the videos and fill the quizzes to make up for the live attendance. And you must, if you're here live, for it to be counted as one of the attendance, you have to stay in for more than 30 minutes on Zoom. So as I mentioned before, today is week 4 of MagMedX on transfer learning. In the previous 3 weeks, we've gone through classical machine learning, some basic PyTorch, and fully supervised medical image segmentation in the last week. And this is last week of the phase 1, and starting in phase 2, we'll dive into more state-of-the-art concepts and methodologies, which we'll talk more about tomorrow. And if you go on our website, under the Program 2023 tab, you'll see the lineup for this week. Great, so here I am happy to introduce our speaker today, Dr. Mohammad Havaei. He is a research scientist at Google, specializing in the development of responsible algorithms. His primary focus lies in comprehending and mitigating potential harm associated with generative models. Throughout his career, he has demonstrated expertise in representation learning, domain adaptation, and meta-learning, primarily in the context of tackling challenges in medical image analysis. He obtained his PhD from the University of Cherbourg, working under the supervision of Hugo Laroche and Pierre-Marc Jordan. Thank you so much, Mohammad, for being here. Second time as an invited speaker for MagMedX. Please go ahead and start sharing your screen. We'll have a Q&A session at the very end. Thanks.
All right, thank you very much for the kind introduction, and thank you for having me. Do you see my screen well? Just to check. Excellent. Okay, so today we're going to talk about generative models and the importance of generative models. I think this year has been more pronounced, I would say, this year and last year compared to previous years. And the reason is with all the advancement in diffusion models, transformer-based models, and but however, these models essentially use as their, like a lot of these models, for example, diffusion models, as their the algorithm and the way they solve the generative modeling and modeling of P of X, they use variational inference for that. And you could actually think about a diffusion model being a stack of essentially hierarchical VAEs, variational autoencoders. And so understanding VAEs and understanding how variational inference works, it kind of helps us to have a better view and have a better high picture of like generative models and what probably future generative models. Okay, so essentially you still see the screen changing, right? Correct. Yes, I see. Great. So why are we interested in generative models? What's the importance of them? So there are like many applications you could think about generative models. One important one is density estimation, right? You want to uh, model the density function of your data, right? You want to see where, in which parts of the data you have a high, like a more dense population, which part of them they're underrepresented. You want to, and you want to kind of learn this distribution over your data. And this allows you, one advantage of having a good generative model would be to, you could sample from your data and even generate samples that are essentially don't appear. And the idea would be to generate samples that don't appear in your data, but they could have been part of your data distribution, right? And there are various reasons why you want to do this. One of them could be for privacy reasons, right? Well, I think a lot of the talks in this workshop are from medical domain, and in medical domain we have this issue of privacy. And so you want to learn like you want to learn the features that are important to you, right? And you want to generate images that have those or represent those features, but essentially you don't want to jeopardize the privacy, and you don't want to kind of go beyond the privacy rules or constraints that you have. So generative models could be a um, good way to sample from your data without, but sample new non-existing samples of your data. And one other reason could be for outlier detection, for example, and this could be like, this has a lot of applications, for example, for anomaly detection, for finding out of distribution examples, right? So this also like an example here, this like a toy example for this. And you could also use it for simulation and learning on synthetic data. And we at the company that I was at previously, we tackled generative models for this particular reason, because in medical imaging, you don't have a lot of data that you care about. So you have a lot of, for example, healthy data. You could have a lot of healthy data, but a lot of time you want to have examples with a specific anomaly, with a specific disease. And a lot of times you don't have those, or you cannot actually train with those because of the privacy concerns. That's why you could use generative models to augment your data, or actually train on synthetic data. And nowadays, I think a lot of people know generative models by the artistic style generation, or essentially um, with the advent of new generative models, they're in a stage that they could be used for content creation, for art, music, even movies. Right now, they're being used, and also they could be used for design. Like here you have, I think, the famous example of an armchair in the shape of avocado. This is from Dali. And you could also have it in, like style transfer. Like you could have the same object in very different environments, styles. And this could also be very helpful for training a neural network also, to generate counterfactual examples. So there are like many reasons why we would like to use generative models. So there are like there are different technologies or different kind of generative models. Um, we have the variational autoencoders, we have generative adversarial networks. These are the probably the most well known, but the list is much more exhaustive than what I present here. So today we're talking about variational autoencoders. So variational autoencoders are a type of latent variable models. And the idea of latent variable model is to learn a mapping from a low dimensional latent variable, for example, z. By the way, do you see my cursor? I could,
Yes.
does the, okay. Let me see if I could also have, yeah, okay, but if you see the, yes, I think this is better. Okay, so we have a simple latent variable model. And sorry, we have a simple latent distribution, right? And you want to learn a mapping G that takes you from that small latent distribution to your more complex data distribution X, right? So Z is very simple, is a simple distribution, and which you can easily sample from. For example, it could be a unit Gaussian, right? A low-dimensional unit Gaussian. And you want it to encode the information that you care about in a disentangled way, right? So an example of this would be this data set of Fraser faces. So a generative model has been using a VAE. A VAE has been learned on this data set using latent variable models, using VAE, I think, in this case. And so it has, you have a noise distribution or a latent distribution that has two axes. Essentially, it's a two-dimensional latent space. And in one, and as you see, the features here are disentangled from each other. You want your latent space to encode two features, essentially, the expression and pose, right? And this is where you see the power, for example, of latent variable models, where it allows you to disentangle these features in a very controllable way. So, for example, as you sample, so if I sample, so the way if I want to interpret this figure here is that if I sample my Z here, right, and then use G to generate it and take it to my data distribution, it will give me this image, right? And then if I move along the Z1 axis, keeping Z2 fixed, I will see that the pose is changing, right? And if I, yes, or like it actually, it's, sorry, it's not pose, it's like two features of smiling and frowning, it seems. Yeah, so essentially one of the features are the same, the other feature is changing. That's kind of the important thing. And if I move along the Z1 dimension, if I move along, sorry, the Z2 dimension, then I see that one of the features is fixed and the other one is kind of frowning here. And this allows you to, this is what we call like disentangled features. So that's kind of how you want to use you want to use latent variable models to kind of encode that information into your latent space. By the way, if there are any questions, please feel free to interrupt me and ask questions so we could have a more interactive session. Right, so essentially the way latent variable models work is that we're interested in modeling P of X, right? We're interested in learning the data distribution. So P of X is what we're interested in. And we want to do this because it's a latent variable model. We want to do this with using a set of latent variables Z, right? And to essentially present the factors of variation in the data distribution, right? So like as I said here, our Z, every dimension in Z would correspond to a factor of variation, right? And so essentially we rewrite this likelihood of X by a joint distribution, right? Where Z is essentially encodes the factors of variation, and we use the Bayes formulation to write it in in the form of product of the likelihood and the prior over our latent space, right? So essentially, our likelihood is factorized by parameters theta, and this we show it by this function g. It's a function of our latent variables, and it's parameterized by these parameters theta. And this is what we want to learn, right? We want to the goal of generative model is to learn g, essentially to learn these parameters theta that take z and then take us to the data distribution. Now, the problem is that we don't know what z's correspond to which x, right? And so if we knew what z's correspond to which x, then we could learn this g by actually like supervised learning, right? We knew this z corresponds to this x, so we could do this mapping, but we don't know, right? So the art of variational, or like the trick of variational inference, like the way it does, is to discover the z's corresponding to like different x's, right? So variational inference aims to discover z's, and to do that, we need to kind of model the posterior p of z given x, right? Now the issue is that finding this posterior is actually very expensive, right? Because you need to kind of go over all of this z space, which is kind of impossible to do. It's very, very expensive. And therefore, what Auto-Encoder does is they actually try to approximate p of z given x. So essentially, the VAE solution is to approximate the posterior with another function, right, q. And so this means that we're going to use a neural network with parameters phi, right, to infer the approximate posterior distribution. So, and we're going to kind of estimate p of z given x using this q of z given x, which we have learned using a neural network, for example. So the question now, the question becomes how to train this q of phi function, like how to train this approximate posterior. And the way that VAE does this is they use autoencoders, right? Any questions so far? All right, so let me recap very briefly, just so because it's like part of first part of it is finishes here. So I'm going to do a recap so we're all on the same page. Right. So as we were saying, to learn a generative model, where we need to have essentially we need to learn this likelihood function, right? This is actually given we sample our latent space to get to the data space, right? So we need to have this function g that takes us from z to x, right? And to kind of learn this function g, or like to model our p of x, we need to have access to z. We need to know like how to sample z, like what z corresponds to which x. Now, because we don't know which z corresponds to which x, we need to kind of discover z. To do that, we need the posterior distribution, but because it's intractable, we estimate it with a function q, right? We kind of approximate it with a function q. So the question becomes now how to kind of learn q, how to use, how to do this posterior approximation using q. And VAE does this with the autoencoder architecture, using the architectures of autoencoders. So let's the next step would be to understand the architecture of autoencoders. So this actually, the autoencoder architectures came out a lot before VAEs, I think in 2009 or 8. And so the way they work is that you have an encoder and you have a decoder. So you essentially want to reconstruct high dimensional data and passing that high dimensional data through a low dimensional bottleneck, right? So to do this, actually you have an encoder and you have an encoder and you have a decoder, right? You pass your like high dimensional data through the encoder, and by doing so, the model the encoder learns what are the information that are important and what are the information that it could lose. So Z, essentially, because it's a low dimensional bottleneck, it has a lot less information in it than X does, right? But then the decoder actually tries to reconstruct from Z, it reconstructs your original data sample, X prime, right? So the goal is actually to have a perfect or have a good reconstruction. And essentially, the goal of encoder would be to kind of understand what are the information it can keep, and sorry, what are the information it can lose, because it needs to lose some type of information. You know, it cannot encode all the information. It needs to lose because this is a low dimensional bottleneck. So the encoder would learn what are the information it could afford to lose. So it would keep kind of the most important information for that example X, right? And the decoder would kind of learn what, given my this latent code, how can I reconstruct my X in a way that kind of is representative or it's faithful to the original example. So the decoder is going to learn the most important information in your whole data set, right? So the encoder is mostly on the example level, and the decoder is kind of how can I, it's on the data set level. This is kind of how you could think about it. And so I have another slide here that kind of gives an example for this. Yeah, so essentially, the encoder is going to learn what information to lose and what information to keep, and the decoder is going to learn how to reconstruct the original image from the bottleneck. And you see here, for example, your low-dimensional bottleneck is kind of like a map of your original data. It's like the way I see it sometimes is that if you look at, for example, Google Maps, and you have two versions of it, the satellite and then you have the map, you see like the map version of it has it has a lot lower information in it, but it contains the most important things, the most important information there. Right. So that's how autoencoders work. And to train autoencoders, essentially, you could do it with essentially you need to have this loss function to train autoencoders, and you could use mean square error, and you could also use binary cross entropy in a lot of cases, because you usually normalize your data between 0 and 1, and you could doing that you could use binary cross entropy as well. Any questions so far? Let's see if there's I don't see the chat here.
I don't see any questions right now, but I guess I'll ask one before we move forward.
Okay.
So if you go back to the architecture of the autoencoder, eventually, would it be the
where did we go? Yeah. Yep.
Yeah, eventually would it be the a low dimensional bottleneck that you if you have a downstream task after the autoencoder, would it be the low dimensional bottleneck that you're eventually trying to optimize back and forth to for the end-to-end training of the downstream task? Let's say
It
whatever.
depends on the downstream task. Like so, for the autoencoder, for the for the problem of autoencoder,
Mhm.
essentially, so the problem that autoencoder tries to solve is essentially optimizing this objective, the mean square error objective. That's how the problem is reconstruction for autoencoder. Now, if you essentially you could use this in other more kind of say like in another you could plug in a downstream task to this, right? A supervised, for example, if you had a supervised problem of classifying something, right? You could essentially add this z, right, to your do you see my, yeah, you could
Yep.
add this z um, and use the features from Z to solve your downstream task. You could do this, yes. And
Mhm.
then this Z would have a direct grade, like direct, your loss functions would actually affect only Z, but not your decoder part.
Right. I've
Yeah,
also seen.
but like for autoencoder itself, it's like an unsupervised learning problem, right? You
Yeah.
want to kind of learn good features from your data set without having any supervised signal.
Right. And Z will be eventually the good features that were learned through the reconstruction process and deconstruction process. That
Yeah,
could be.
in the autoencoder setup,
Mhm,
yes. Well, they actually do this also in the VAEs as well,
mhm.
but yeah.
Yeah, I've also seen applications on denoising using autoencoder. Um,
Yeah, so that's actually, yeah, so that the a denoising autoencoder, one way to train your autoencoder is to use the better way for it is to use a denoising autoencoder to essentially train it. This is the reason I mentioned this is because I'm kind of taking a point from this for the variational autoencoder.
mm,
But if you were just interested in the autoencoder without the stochasticity of VAEs, then you would actually the way you would do it is to make X noisy, right? And then your X prime would try to reconstruct the original unnoised version. So your
okay.
loss function would be the same. It's just like here in the intermediate, you would have a noise transformation. It's like, right? So this would actually help your autoencoder to learn more discriminative features and
Let's say
not.
that let's say that the input is already noisy, whatever it is, like a noisy CT image with a bunch of artifacts, and your output, the reconstructed image can be higher resolution without
Well,
the.
you need to, yeah, but then you need to have somehow how this. I would say it depends because you would need to kind of optimize this loss function here, right? And this loss function here is essentially a mean square error. So you would need to have some target uh, that you could that you could optimize, you
Right,
know?
right.
So like if you can find a way to get this target, then yes,
Okay.
you could do it.
Right. We have a bunch of questions coming up now as well. From Soraya, is there a one-to-one mapping of the input and the reconstruction, or is there some variation in what gets output given the input image?
So for the autoencoder, so that's actually a good point, and we will get to it. So autoencoder, there is no stochasticity in autoencoder. Like the plain vanilla autoencoder does not have, it's a deterministic network. It doesn't have any
Mhm.
stochasticity. So yes, your X would give you one code Z, and then your that deterministic Z would give you a deterministic reconstruction.
Right. So let's say like a very naive question of choosing autoencoder as a model to solve your problem. If the point is to reconstruct the inputs, what are the applications that are most used?
Yeah, so I would say I guess the most successful application of autoencoder is variational autoencoder.
Right.
And I would say whatever it is that you want to use autoencoder for, probably variational autoencoder, because it has this notion of stochasticity in it. It works also as a type of a data augmentation for you. So you could also try that. But a lot of times, a use case of autoencoder is to learn unsupervised features from learn features in an unsupervised way from your data set. Think like you have a bunch of unlabeled data, right? For example, in medical imaging data sets, the probably most expensive part is to annotate the data. So assume you have this huge data set of MRIs, and you have a little bit of essentially how to say annotated images. So one thing you could do, you could first essentially learn this autoencoder on your unsupervised data. This will give you a feature extractor in your encoder, like given X, what would be the features for that, like X, that it's kind of learned from the entire unlabeled data. And then you can use your, how to say, smaller data set, which is supervised to kind of learn to learn a classifier on top of your Z.
Right. Thank you. Edward has a question. What are the downsides encountered so far using these autoencoders?
What do you like? What are the problems with it? Downsides of it?
Yeah, I guess that's what he meant.
It doesn't. So the autoencoder is like it's. So I've tried it a lot. It doesn't really work unless you have like a huge amount of data. And autoencoder itself, without the denoising part. So so there are like two type of problems. Controlling for what function, because one issue that you may encounter is that your autoencoder might learn an identity function, meaning that it wouldn't learn any interesting features from the data set. It would just learn the identity function without learning any meaningful features from your data, right? And this happens a lot of times if this low dimensional bottleneck is large. So you don't want to have a very large type of a bottleneck here, because it would encode the identity function. And if your bottleneck is very small, then it wouldn't be able to kind of learn a lot of meaningful, probably. It would require a lot of, the size of the Z could be sensitive to the task that you're trying to solve. And also this architecture itself, without any stochasticity, doesn't work very well, I suppose. Like this is something that I've encountered. So I would say if somebody wants to use autoencoders, then I suggest using denoising autoencoders, and maybe check variational autoencoders, because they have this notion. Because they have stochasticity inside, both denoising and variational autoencoders. Therefore, they're less probable to overfit to your data. So yeah, I would say it doesn't really work very well as a to use by itself without any further regularization.
Right. Thank you. Greg has a question. In general, how are Z features decided? Does the model find them or are they determined a priori?
Sorry,
The bottleneck.
can you repeat that question?
Yeah,
I was
Greg
looking
was
at the chat.
right.
Yeah.
Yeah, there's a lot of questions popping out. So Greg was asking, in general, how are the Z features decided, the bottleneck Z features? Does the model find them unsupervised or they are determined a priori?
So yeah, they are determined a priori, and the way it's a type of a, you could think about it as a type of a hyperparameter, and hyperparameters are essentially variables in your network that you like try different things and see which one works well.
Right. So the unsupervised part of autoencoders doesn't apply to it doesn't apply to the Z feature bottleneck part because that part is one of the hyperparameters. Then the unsupervised.
Yeah. So the unsupervised part is essentially so the unsupervised part is essentially not having like labeled data here.
Okay.
Yeah, but you need to, because essentially you're reducing, this is the low dimensional bottleneck, right? So you're reducing essentially the dimension of your X to something lower. You need to kind of know how much information you are willing to lose, how many bits of information you are willing to lose. This is
Right.
something that you would need to determine a priori.
Right. From Mustafa, can we
Mhm.
say the encoder acts as a feature reduction or feature importance that we use in technique that we use in
Yeah,
yeah, okay.
yeah. So actually, a linear, you could actually prove that the linear autoencoder doesn't do better than PCA.
Oh, interesting.
That's why the linear version of it is actually not very interesting.
Okay. Fatima asked, what specifications should these two networks have? I guess she meant encoder and decoder. Can they be two different network types?
Yeah, they could be. They could be. They could be two different network types. Yes. Usually, the way the original, like I guess the first version of autoencoders, uh, the decoder was transposed of the encoder,
Mm-hmm.
but it doesn't have to be like that. They
Right.
could be very different networks.
And Shakufa replied to Edward. Shakufa is one of our mentors this week. She said that one downside of autoencoders is that they may require a huge amount of data set, and not having that so much of data might result in overfitting sensitivity to change in the input.
Yes. Yeah. So that's a good point, and that's why like things like denoising autoencoders would, by design, encode a type of a data augmentation, right?
Right,
Because for every example, every time every time the model sees an example, it would see it with a different type of noise, right? So,
right,
and it would try to reconstruct the original version. It's like it works really well compared
right,
to the autoencoder. Like if you visualize the features, so you could visualize the first layer features. But these are like very old papers, like from 2008. Actually, I think the paper is, yeah, so these are very old
like
papers.
a
But
linear autoencoder can, if you use it as a visualization of
it doesn't,
clustering
yeah.
features,
Yeah,
you
yeah.
can,
So then, yeah. Okay.
it reminds me of like a UMAP. So I guess they can perform similarly. Okay, sure. Shikufa also, yeah, so she also said it can be seen as feature reduction or extracting informed features from input data similar to traditional PCA. Semi said overfitting is more likely to occur when the model has a larger number of parameters relative to the size of training data set. I think the biggest issue that it might struggle to generalize well to unseen examples when trained on a limited amount of data. Bhumika asked, could you please tell me more about hyperparameters in autoencoder? I think that will be the last question for this little
How
session.
to
Yeah, the
more
hyperparameters.
about hyperparameters in an autoencoder.
Yeah.
Sure. So just one thing about the, sorry, how long is the session generally?
Today you're the only speaker, so we have till 12.
Okay, till 12? Okay, so
Yeah.
I will try to finish it in time. Okay, so just one note about the like dimensionality reduction. So I think it's actually a good point, and the way relates to part of the things that I said before. It's essentially that's kind of the art of autoencoder is to kind of learn how to, as in PCA you have a fixed linear algebra formulation to select the eigenvalues and the eigenvectors that you would like to keep in autoencoder. You learn those from your data. And that's kind of a lot more powerful um, model, or like a lot more powerful way of uh, reducing the dimensionality of your data. However, it would require a lot of data to to learn those, right? Um, so that's kind of the encoder learns what features to keep and what features to lose. So about the hyperparameters, so generally in the hyperparameters are like any other supervised network or any other neural network or any other machine learning network, essentially. So every machine learning network, we do have like some type of hyperparameters. I mean, usually we have, even for decision trees we have, for random forests we have, for SVMs we have, for like neural networks also uh, we have. For example, for neural networks and also like autoencoders, the learning base, one hyperparameters that is very important is the learning rate, right? Because we use gradient descent to learn our parameters, the learning step that we take for every update. It's very important. Another hyperparameter would be the optimizer. What optimizer we use. It's also like, do we use dropout or not? What would be the number of layers in our? So we have multiple layers in our encoder, right? How many layers? That would be a hyperparameter. What would be the dimensionality of our Z, of our low dimensional bottleneck? That would be a hyperparameter. What would be the width? So the depth and the width of encoder and decoder, it's also a hyperparameter. So we have a lot of, like in the convolutional space, like what are the kernels that I use for my convolutions? That's a hyperparameter. The pooling that I use, that's a hyperparameter. Like you could think about every transformation that you use in your neural network could be a hyperparameter. However, right now, the way usually people do is that there are some architectures that have been proven to work well. So the recommendation is to use those architectures that work, like people have mentioned, that work well. For example, you have ResNet 50. You have, for example, the transformer architecture. It's something that a set of transformations or a set of blocks that work together, it's well recognized. So usually people just use what's been used before and don't do exhaustive hyperparameter search. But I would say the learning rate is something that you should always check. So for every problem, there would be a set of hyperparameters that are important. I would say learning rate is among them. For autoencoder, perhaps this dimensionality of Z would be the most important and unique to autoencoders.
Mhm. Actually, we have another follow-up question from Mohammad. Bashikova answered it already. Do you want to answer this one, or do you want to move on and then we finish presentation and
Yeah.
go
So how does it?
ahead?
Oh, yeah. So the binary cross entropy.
Yeah.
About the binary cross entropy. So it is so originally true. Uh, Binary cross entropy, it is originally used for binary, but you could also use it for continuous if your examples are between 0 and 1. Like because yeah, you could do it. There's actually a proof about this, that because your probabilities, when you use binary cross entropies, your probabilities are between, so binary cross entropy maps your probabilities between 0 and 1, right? And if your data falls between like a 0 and 1, then it's equivalent, roughly.
Mhm.
You could, I mean, I do agree it's better to use it for one for binary and the other one for continuous, but I have seen it that it's used for when given that your data is normalized between 0 and 1.
Thank you so much for the engaging discussion here. Yeah, we can talk about the next section of the
Right.
presentation.
So essentially, right. So let's see where we were. Right. So let's go back again to refresh our memory. What was the problem of VAE? So essentially with VAEs, we needed to, with the variational inference, essentially, we needed to know which Z corresponds to which X, right, to formulate this likelihood model, or like this likelihood function, P of X given Z. Now, VAE trains a function, or learns a function Q, to approximate the posterior distribution Q of Z given X, parameterized by these parameters phi, right? And this was because we needed to know which Z corresponds to which X, and the posterior distribution was intractable, so we kind of approximated. Right? So this is to uncover which Z corresponds to which X, as we were saying, right? So the way VAE does this is it uses the variational, it uses the autoencoder architecture, right? So essentially, it uses the encoder, right? So the encoder that we talked about in autoencoder. So the VAE uses the encoder to essentially map our the input example X to this latent space Z. But here, instead of mapping it the way autoencoder did it, to mapping it to a fixed deterministic like a space Z, here, because we are interested in learning this posterior kind of distribution, the encoder needs to map this to a stochastic latent space, right? So essentially, in VAE, X, using this encoder, X is mapped to a stochastic space Q of essentially this one, Q of Z given X. Now, then what we do is that we're going to sample from this stochastic space. We're going to sample an example, right? And then the decoder is going to take those samples, right, and go to the input space again, input space X, do a reconstruction X prime, right? So again, the way it works is that the encoder is going to take us from like X to a latent space Q of Z given X, and then the decoder is going to essentially take us from that latent space to the data space again, right? This is how the VAE uses, this is how VAE works, essentially. And as you see, this is kind of like the autoencoder architecture, with the difference that this space here, this latent bottleneck space, is not deterministic anymore, but it's stochastic. And usually the latent space that we use for assume is a unit Gaussian, is an isotropic Gaussian to parameterize Q. And the dimensionality of this latent space is essentially the length of the hidden variables, which again, similar to autoencoders, is a hyperparameter. So you would essentially try with different lengths of codes and essentially different dimension of your isotropic Gaussian and see which one works best. But the problem here is that how does this look in terms of code, right? This is kind of the question. Here, we're saying that VAE, the encoder of VAE maps X to a distribution, and then the decoder samples from that distribution, goes to the input space again. But how would you do it in terms of code? So the way the VAE does this is essentially, this is how it works. So the encoder actually gives you two, so let me see how to say this. So we're going to, okay, so because we said that the latent space is an isotropic Gaussian, right? So we could parameterize an isotropic Gaussian by two. We can parameterize a Gaussian by two parameters, right? A mu and a sigma, right? And so if the encoder actually outputs, instead of outputting a single z like the autoencoder did, if the encoder outputs two codes, right? One mu and one sigma, together they would act as parameters of a Gaussian. And then we could sample from this Gaussian and essentially then take these samples to the decoder, and it gives us the original examples X, right? So this is kind of how we do this. The problem here is that this sampling here is a discrete process. Like when you sample from a distribution, the one problem is that the sampling here is not differentiable. So the way that autoencoder, yes, so how to sample this without harming the gradient flow? The way that autoencoder does, the variational autoencoder does this, is using reparameterization trick, right? So, and what does reparameterization trick mean? Essentially, it separates the stochasticity from the graph, right? Because here, there is a stochasticity in the sampling, and this kind of cuts the gradient flow from decoder to the encoder. So reparameterization trick brings out the stochasticity from the network itself. And by doing so, you essentially can have the gradient flowing from your decoder to your encoder. And the way it works is actually with this formulation. So you first sample from a unit Gaussian outside of your graph. And then, so in the encoder gives you essentially a mu and a sigma. And then you sample from your a unit Gaussian. And by using this formulation here, by multiplying essentially your sample with the variance, with the variance that your encoder gave, and then adding the mean to it, it would essentially mean that you have sampled from this distribution, right? By using this process here, this would essentially mean that you're sampling from your mu and sigma, even though that essentially you did it outside of your graph, and it doesn't kind of harm the gradient flow. Here, you see that it works like this. Right. So the output of the decoder is actually usually a sigmoid, and that's actually the reason why you could use a binary cross entropy, because it's a sigmoid. in the output. That's how it's done usually. And this, your input is scaled between 0 and 1. That's how it's done usually. But I mean, not necessarily, but if you do it like this, then you could use binary cross-entry. Right, any questions about the reparameterization trick and the VAE so far? Was it clear, or I hope it was clear. Okay, okay. So let me know later on if there was a question about this. Right. So the question now remains: how do we optimize the VAEs? Right? We know that we know how to kind of do the forward pass, and we know how to do the backward pass. The backward pass is done by so we do the forward pass through reparameterization trick, mu and sigma, and then the backward pass. This reparameterization trick allows us to do the backward pass. The question remains now is that what does the objective function look for, right? So the way actually the autoencoder actually works is that it actually, if you do them, if you write down the variational inference math for it, the way it works is that it tries to kind of maximize a variational lower bound on the likelihood of the data, right? This is kind of how generally the variational inference works. Now, if you write down, if you write this down and simplify it, the variational lower bound adds up to essentially leads to two components, like this component and this component. One of them is the KL, and one of them is essentially the likelihood component. And we could then rewrite this elbow in terms of a KL and a reconstruction term, right? So the KL regularization, what KL regularization tries to do is that it tries to essentially map, or it tries to regularize our approximate posterior distribution to the prior distribution, right? And then the reconstruction loss is essentially the loss function we had for the autoencoder, right? So let me talk about this KL and tell you what it does here. Probably it could be easier. So the KL is actually focuses on this area here, and it tries to kind of make sure our approximate posterior looks like a normal distribution. That's what it does. And so why, like in a high level, why do we want that, and why is that important? Is because once you want to sample from your generative model, you kind of ditch the encoder, and you have this part, right? This would be your generative model, right? And your latent space would be a normal distribution, right? So your latent space would be a normal distribution, and you're sampling from a normal distribution, right? So that's why that inside, like in a very high level, you would want your encoder, right? When it kind of does approximate inference, that approximate inference, the distribution of your approximate inference looks like the distribution that you will use to sample from later on, like looks like a normal distribution. That's kind of the like high level intuition why that's the case. But in terms of like just coding and in terms of optimization, you have two components. One of them is reconstruction. So it's the same thing that you have for autoencoder. And the other one is this regularization, essentially, which means which means that the approximate posterior should match the prior, which is which is usually a normal distribution. So the prior is essentially the distribution that you're going to sample from later on. So if you were using in sampling, you were using a a mixture of Gaussians, then later on you would also here would be a mixture of Gaussian, and your sampling would be a mixture of Gaussian. So it depends really. Your prior is the distribution that you're going to sample from later on for your generative model, but usually we just use a normal distribution. So there's a question, how does this z term in equation equals to the actual sampling from the distribution? I meant mathematically. Yeah, so the question is why essentially does this mean that you are sampling from this, if I understand correctly, right? Yes. So there's actually a formal proof on this in their paper that, yeah, I would recommend you to go see the paper for this. Yeah, there's a formal proof about it in the paper. I forgot exactly how this mapping is done. There's actually a nice intuitive way to explain it, but the formal definition, you can find it in the paper. The formal proof. Could you provide some examples of use cases? I don't understand like this. What do you mean? Which use cases of what? Yeah, this part is, can you explain a bit more use cases of VAEs? We will get to some use cases of VAEs later on. Let me think about this mapping here. I don't think it's kind of difficult to show it. But yeah, I think you can easily find it in the paper. Right. So why reparameterization makes backpropagation possible? Yes, because you're essentially doing this. Okay, because this one, when you're sampling, okay, here, when this doesn't depend on anything of your graph, right? It's not can say it's not traced in your graph. This sampling. So the sampling function is done here, right? It's kind of outside your graph. This doesn't depend on anything inside your graph. That's why. Whereas if you wanted to kind of sample from this directly, then these two are actually outputs of your graph. That's why you couldn't backpropagate. But because of the reparameterization, the sampling process or the stochasticity is outside the graph. I think this slide kind of wants to explain that. Right. So yes. From the math equation given, it means nonlinear parts of the image are nonlinear parts of the images are linearized to get more info from the image for the reconstruction, right? Which with the nonlinear part, I mean the curved part. I don't understand the curved part. Can you? Yeah, this one with nonlinear part, I mean the curved part. From the math equation, it means that the nonlinear parts of the images. Yeah, sorry, I don't fully understand the question here. If anybody understands it better to explain, I would appreciate. Yeah, but to give it like to explain this in a very high level and an intuitive level is that an autoencoder only has this reconstruction part, right? VAE essentially has this regularization part because it has this stochasticity inside of the bottleneck, right? Because your bottleneck essentially is not a latent, fixed latent code, it's a distribution. And you want that distribution to behave in a certain way. You want that distribution to look like a unit Gaussian. That's why you have this regularization term here. You have your KL here. So because you kind of want to control your distribution, you want your approximate distribution to look like a unit Gaussian, or you look like a distribution that you can later on sample from, or like you know how to sample from. That's exactly why we have this regularization term here. Right. So we talked about this. Oh, sorry, we're going. Why are we? Right here. So usually, actually, just one thing. So one thing about VAEs is that not only like mathematically, right? Mathematically, every output of VAE is actually not only the approximate distribution and not only the approximate posterior distribution is stochastic, right, by design, but also like we have actually, so in VAE we have two distributions. We have the likelihood distribution, which is P of x given z, and we have Q, which is Q of x given, which is Q of z given x, right? So Q of z given x is here, this one, right? So we have this distribution here. Output of the decoder is also a distribution. It's the likelihood distribution. Whereas that's also another difference with autoencoder. With autoencoder, the latent space is deterministic. The output of the decoder is also deterministic. However, with VAE, both of them are stochastic. Both of them are actually distributions, right? But in terms of coding, a lot of time, people just use x prime as the output of the decoder. They just put a deterministic function here, right? They ignore essentially, they ignore the variance, even though that usually you shouldn't do that, and you could actually learn the variance, and it does help. But because it increases the parameters that you have to learn, because for every essentially element in your x, you will have a distribution, right? And so that means increasing the parameters of your decoder, at least the final layer, doubling it. Therefore, people just a lot of times they assume a fixed or variance, or they just totally ignore the variance, meaning that they assume a variance of 1. And they just output the mean. And therefore, they ignore this distribution here. But mathematically, the output of the decoder should also be a distribution. Right, because it's what you're trying to do. You're trying to learn the data distribution, right? So it's it makes a lot of sense to learn the variance. Yeah. So sampling. How does sampling from a VAE looks like? So we talked about this a bit before. Um, So the KL divergence in the VAE loss forces the distribution of the latent space to look like the prior normal distribution, something that we talked about before. At sampling time, so this would allow the output of the encoder to look like a Gaussian distribution, right? Now, at sampling, that would be the marginal posterior distribution. The marginal posterior distribution would like actually a unit, a normal distribution, a unit Gaussian. Now, at sampling time, we remove the encoder part, right? And then sample from the prior, right? So if you remember in the reparameterization trick, right, we were sampling from the a unit distribution, right? So we kind of do exactly the same thing, right? We remove the encoder. So if can I just go? I don't want to like do. So here, we remove everything here, and we have this one, right? We have this one. And we remove everything about the mu and sigma and everything about the encoder. Sorry. Yes. So we have, and because we have the KL, right? The samples that we take, because we use the KL to kind of make our posterior distribution similar to a Gaussian distribution. Then once we sample from this Gaussian distribution, the decoder can interpret our samples in a coherent way. And it will give us images that look like samples from our data distribution. So here are some samples from a VAE once it came out. I know that for the current state of generative models, this is just a joke, but at the time they were groundbreaking. So this is from a data set of faces, and this is from ImageNet. Yeah. So let's, because we talked about autoencoders, I talked about this a bit before, but to make it more concrete and to kind of compare again the latent space of autoencoder and VAE, let's talk about it a bit more. So the difference between autoencoder and VAE, essentially. So the difference is that the autoencoder, similar to VAE, autoencoder also makes a compressed code of the input, right? However, it doesn't give a distribution. It gives a fixed space, right? And so one question could be that, okay, why do we need the VAE? Why can't we just use autoencoder and then sample from Z? Sample from our, we sample from this latent space Z here. The problem is that we don't know how to sample from the latent space of an autoencoder, right? As we said before, it doesn't, because it doesn't have this KL to regularize this Z space to a distribution that we know how to sample from, like Gaussian distribution. We don't, with autoencoder, actually, we don't know how the distribution looks like to sample from. So here, you could see this is the latent space of an autoencoder. You see that even though that we have good separation of clusters, so it does actually learn how to kind of map or how to cluster examples that look similar together, close together. So it's learning meaningful features, the autoencoder. However, it doesn't look like a distribution, right? It's not like something that we could sample from. So this is if we use autoencoder, or if we use VAE with only the reconstruction loss. So they would actually be the same. Now, in the middle, if we only use the KL, right? So if we don't, so the VAE has two loss functions, right? The KL, the regularization, and the reconstruction. If we use the reconstruction, this is what we get. If we only use the reconstruction. If we only use the KL, this is what we get, right? So what the KL does, the KL is trying to make this Z space look like a Gaussian distribution, right? So we call like our marginal posterior looking like a Gaussian distribution. So what does a marginal posterior mean? Means that if I map all of my examples in my data set to the Z space and show the latent space, what the latent space looks like. That's kind of what we say the marginal posterior, right? So every dot here that you see is an encoded code from my data set. So I take one image and use the encoder and then visualize it here, or like sample from it here. But in VAE, if I use both the KL and the loss function and the reconstruction, this is what I get, right? So essentially, you could think the way these two components work together is that the reconstruction loss wants to kind of use the space in a way that does perfect reconstruction, right? So if I don't have any KL, if I don't regularize the space, then the model is just gonna place different examples in a way that it's going to do a perfect reconstruction job, right? So that's actually why overfits, because it does like really a perfect reconstruction, right? With the KL, it doesn't care about reconstruction anymore, right? It just tries to focus to have a good unit distribution, like a Gaussian distribution, right? So they are kind of fighting each other. They are in adversarial connection with each other. KL is trying to put everything in it doesn't care about the reconstruction. It tries to put everything in Gaussian distribution. Reconstruction it tries to fight the KL in the reconstruction and tries to put everything close together in a way that helps the reconstruction. With VAE, when you have both of them together, you're hoping to find a sweet spot where you have both, right? You have examples, so every color is like a different example, a different class. You have examples of different classes kind of falling or like mapped close together, but the marginal posterior, you see that it looks relatively like a Gaussian. So this actually brings us to one problem with VAE. So as we were saying here, is like the KL and here it kind of talks about the same thing. The KL and reconstruction kind of are in adversarial connection with each other. This is what the reconstruction wants to do, right? Because it kind of wants to separate. So the reconstruction, the way it does perfect reconstruction is that if examples of every class are far away from each other, if the clusters are far away from each other, then it does a perfect reconstruction. That's kind of how it works. And the KL wants to kind of map everything together. So with KL, we want to regularize this the reconstruction loss in a way that kind of we could kind of interpolate our examples. You know, we kind of populate the entire space. So if you move between classes, for example, here you have a square, here you have a triangle, you have kind of a mixture of both. You could interpolate between your examples, your classes. That's why, for example, in VAEs, you could, in the first examples that I showed, you could smoothly, this makes it kind of the space smooth, right? You could kind of sample from the entire space if you have the KL. If you don't have the KL, you have a lot of empty spaces here. You cannot sample from the empty spaces. Kind of creates a trouble for a generative model, because you want to have this smooth, you want to populate the entire space. That's what the KL does. So, and a follow-up work to beta VAE is, sorry, a follow-up work to VAE is what we call beta VAE. So we were saying before that there's this adversarial connection between, adversarial relationship between these two loss functions, the KL and the reconstructions, as I mentioned before. So the beta VAE, what it does is that it tries to kind of find the sweet spot. With the VAE, there is with beta VAE, you're essentially trying to, you put a weight on your KL, so you could essentially control the amount of regularization that you have on your VAE. So in a vanilla VAE, in the mathematical derivation, it doesn't give you any coefficient here, right? But with beta VAE, they've introduced this the weight or coefficient of the KL, which kind of helps you regularize the space better. So an example of why this is important, yeah, so if beta is equal to 1, you get the original VAE. If beta is higher than 1, it puts stronger emphasis on the KL, makes the space smooth. So in a normal VAE, you have a lot of holes, because even though that the KL is trying to make this smooth, but still the reconstruction is usually more powerful because it's a lot higher dimension. It's usually more powerful, and you end up having a lot of holes in your marginal posterior space. With beta VAE, you kind of try to regularize the space more, which looks more like a Gaussian. And this essentially helps to disentangle your latent space a lot more. Any questions so far? So I'll just wait like maybe 30 seconds for questions before moving on. Okay. Yeah, so the next section is going to be like maybe 1 or 2 applications of VAEs in medical imaging. Okay, I hope it was clear. Right. So one application that you could use VAE is like one of the use cases that you could have for VAEs is to kind of learn a shape prior, like learn a prior over your data, like essentially, and that becomes very important in a lot of applications where, for example, they have a anatomical shape prior, right? For example, a heart. There is a prior. We could imagine a prior over what is anatomically plausible. And in a lot of other applications too, like we could use actually unsupervised learning models generally to kind of learn a prior over the data. And VAEs, because they have this notion of because of them being more regularized than autoencoders, then there are a better choice for this. Right. So essentially, this paper here, they want to provide a kind of, they learn an anatomical prior for the for cardiac segmentation, for like what would be a plausible anatomy for for cardiac segmentation. So the way they work is that one problem that segmentation has is that when you do segmentations, sometimes you have a lot of like imperfections in your segmentations, which don't anatomically don't make any sense. Like you have holes in your segmented region, or you have for example, some holes here, some parts that don't make any sense from the anatomical constraints, right? So the proposal was that they actually use variational autoencoders to learn a prior over the ground truths of cardiac segmentations, like cardiac labels, like segmentation maps. So the VAE is actually trained on the ground truth, segmentation ground truth. So the task here is cardiac segmentation. You have like you have, I think, is it a CT or an ultrasound? And then the goal is to generate these segmentation maps, right? So essentially to kind of learn a prior over these, what anatomically plausible segmentation map could be. They learn, they use VAE for that. And then essentially they populate, they essentially use, they populate the latent space. So they have limited amount of data, but then they do rejection sampling to populate their latent space. And so later on, when they have a segmentation method, and then they have the segmentation map, which is imperfect, what they do is that they infer a Z, right? And essentially they kind of map, they see which of these populated samples in the latent space their inferred Z is closest to, right? And then they use that one as the final segmentation map. So they use the codes for that latent code, and they decode it, and instead of having the latent code that they inferred from the segmentation map, they use the closest one in their populated latent space. This kind of so you in a way, this gives them guarantee that whatever output that the decoder gives is anatomically plausible. So that's kind of the high level of it. For details, you could look at the paper for more details on like how this rejection sampling works. And so here are some examples. You have, it's an MRI. You have your input MRI. The ground truth looks like this. The prediction of the segmentation map looks like this, right? And then you could think about this process as a post-processing on top of your segmenter. And after the post-processing, using this prior network that they have learned on the ground truth, they have very kind of much better results. I think this was a kind of like a different way of using VAEs than what I usually see in the literature, which I thought it was interesting. Another example of using VAEs is essentially, so UNet is actually a model that's used a lot for segmentation. You probably have seen it a lot. So probabilistic unit is there to deal with intra-observer and inter-observer variability. So the issue that we have a lot of times is that for every input example, for every, like when you give an image to different experts to annotate, right? The ground truth segments, the ground truth segmentations by different annotators is different, right? Even if you ask the same observer or the same annotator to annotate an image in different times, like with time intervals, it could be that they would give you slightly different ground truth segmentation. Now, this doesn't necessarily mean that one of them made a mistake. In fact, a lot of times they are happy with the annotation that they made. Means that the image was the variability means the image was actually expensive. Yes, the variability means that the image was actually very difficult. And so usually the way that a lot of papers or a lot of methods work is that they take the intersection between different annotations. This paper actually proposes to kind of use that ambiguity, right? And so the idea would be that instead of the segmentation model giving out a single output, right? The segmentation model could give a distribution, which would allow you to sample from. So it wouldn't be a one-to-one mapping anymore, your segmenter. It would be one-to-many mappings. So it kind of accounts for the uncertainty of annotations. And the way this works is that the goal would be to, given an input image, you would have a prior network, right? And that prior network would give you a latent space where you could sample from. So this latent space is essentially dependent on that input image, right? Whereas the previous VAEs that we saw, the prior distribution was fixed, was a normal distribution. Here, the prior network is actually a neural network that you can learn, and it depends on your input image. And then having that prior network, it gives you a latent space. And so this would be your prior distribution now, which depends on your input image. And then you could actually sample from this latent space, and you just concatenate the samples that you got with the output of with the final layer of or one of the final layers, or multiple final layers of your segmenter model. And this essentially gives you some stochasticity in your network and kind of gives you a distribution of outputs. I felt like this was a very interesting take on accounting for uncertainty in your input image.
Can I ask a question?
Sure, yeah.
Yeah, this is very interesting to me, especially for the interoperability problem here. My question regarding to the evaluation method for determining how well the model does after you have this probabilistic U-Net prediction. Let's say that you have the latent space, a distribution of samples from Z1 to Z3. I don't know, here it's a second last layer of your U-Net, and then how many predictions are you actually having at the segmentation mask output, and how do you determine the final die score of this?
Yeah, so they use let me see, to compare essentially. Yeah. So they essentially, the more Monte Carlo samples that you get, the more that you take, the better coverage of the distribution you will have, and the better. So there's the input, essentially for every example, because you have different annotations for every example, you have a distribution, right, for every example. And then your output would also be a distribution. And the way you essentially compute, the way you evaluate, is to essentially you evaluate how well you cover that distribution.
Okay. I'm
So they
gonna go
use
through
they
this
use
paper.
squared energy distance
Okay.
with the ground truth. That's so they don't use dice score because dice score is kind of like comparing two things together,
Right.
right? Here you're comparing kind of like distributions.
So even the input, the ground truth is also a
A
distribution.
distribution, yeah. So you have, so I think in that data set they don't have a
Oh,
lot
because
of
you have
examples,
multiple observers. You
annotators.
have multiple ground truths. That's why you also have a distribution of the
Exactly.
ground. Great. Okay, I see.
Yeah. But you don't have a lot of them though. So it's like it's kind of like a very noisy distribution. If you,
Okay,
I think you have
gotcha.
like 5 or 6 examples.
Right. Great.
But the goal would be if you can cover like the modes. The way the evaluation is that if you can cover the modes determined by those essentially the annotators
Mhm.
outputs. Yeah, and the way they train this is that they use the ground truth model. So every time they sample an image from the ground truth, right? Where for every input example, every time you see an input example, you have a distribution of ground truth. You just sample one of them, and then you kind of have this posterior network that you train together with your prior network, right? And then the goal would be to kind of match these two distributions together. And then they have some regularization methods so they wouldn't collapse. And yeah, and then at the inference time, or like the yeah non-training time at the test time, for example, they would just drop this posterior network and only use the prior network, like seen here. So this works well with you, relatively well, if you do a lot of Monte Carlo samples. But I think the application was interesting here as well. Uh, So let me see if there are any questions. How many times we should create annotations for one sample to make sure? Yeah, so that's the more, essentially the more you take samples, the better it would be. Usually with this stuff, you need to have a lot of samples. Yeah, so you will have a conditional. So I'm also just one thing here. This works with it's not like your prior is conditioned by the input. You have a conditional prior. Yeah, this is your segmentation model. And then you're by sampling from the latent space here, you're adding stochasticity leading into one-to-many mappings. I think this is just for later, this slide for later. Yeah, and then the more samples, the better. Right. Okay. Thank you for the paper. For that other paper, let me just check that paper too because I want to read it. Yes. Okay. Yeah. So there's actually a lot of work on variational inference can be done for essentially partial observations, right? So if you have like a very good, so denoising autoencoder essentially is actually a method that can deal with partial observations. You could think about it like that. And there's a lot of work. Part one, a good use case of generative networks is actually because they learn the distribution of data, right? So you could actually kind of infer, given part of the data, partial observation, you could infer how the missing part would look like. And latent variable models, because they have you could infer posterior distribution, right? It gives you a posterior distribution of what the missing parts of the input may look like. So we had a paper about this. It was published in, yeah, we did have a paper on this where, for example, you would give a crop of a face, and then the generative model would kind of infer with various degrees of uncertainty. And this is kind of the interesting part about variational inference, because you could actually get meaningful information. You could use this posterior inference that you get, because given given an input, partial observation, right? You would essentially you would get the posterior inference over your entire output space. Your Q of z given x, your z would be on the entire space. And it would actually, so the model would say, is like, what uncertainties I can infer from my output, in my output space, given using the latent variables, given the partial observation that I have. So they can be very powerful and very interesting for essentially computing uncertainties on missing part of your input space. Right. So just one couple of notes about evaluation of generative networks. So because VAEs compute likelihood, right? So you could actually use likelihood to compute the essentially to see. You could compute the likelihood over your data set to evaluate your variational network. And so this is how you could do it. Essentially, you need to sample a lot of, the way you do it is that you sample a lot of z's from your input space, and then you compute the likelihood over these samples. And so that's one way to do it. The other way is, instead of computing the likelihood, you can compute, you could evaluate your generative network on the samples that they make. So there are like two types of evaluations. One of them is qualitative evaluation. The other one is quantitative evaluation. So quantitative evaluations, essentially, you want to get like actual numbers, comparing. Usually the way it works is that you want to compare, you have the distribution of your input examples, like data distribution, and then you have the distribution of the generated examples. And then you can compare different statistics. You can compare FID, you can compare KID, and then you have inception score as well, where essentially you have a pre-trained network, you have a pre-trained classifier, right? And then you can use the inception score to evaluate how diverse your generated examples are, right? So essentially, it has the component of seeing, evaluating if your model is generating examples only from one class, or if it's generating examples from like all the classes uniformly. And that's, you kind of want your model to generate examples from all your classes, not just from one class. So that's kind of, the inception score is good for that. You have also qualitative way of evaluating. For every input example, for every generated example, you could kind of crawl your data distribution and kind of see or find the nearest neighbor to that generated examples. You don't want the model to memorize any examples from your data, right? You want them to be different. You want them to be at least a little bit different. So if your nearest neighbor from your data distribution is very similar, or like kind of copied by your generative model, then it's kind of like overfitting, and it's your model is memorizing the data. Your generative model is memorizing the data. Human rating. So there's, in terms of human evaluation, there are actually two ways to evaluate your model. One of them is crowdsourcing. So you ask a lot of annotators, human annotators, to essentially see if this is a good image or not, or if this is if this image, how to determine good is kind of dependent on your criteria. One way is to ask the human annotators if this is a generated example, or if this is a data from my data distribution, right? And if if they can distinguish that this is generated or this is from your data distribution, then that means your generative model is not doing very well. But if they get confused, then generative model is doing well. There's another way of actually human annotator is actually asking them for more complicated questions. If this is a harmful image, for example, if this generated image, is it representative of, for example, a type of a cultural event? For that, you could have surveys or you could have focus groups. So the way it's done a lot of times is that you have like 10 people in a meeting and discussing every single image. So it's not very scalable, but the level of evaluation, the quality of evaluation would be very high there. Yeah, and then you also evaluate different things by looking at the data. A lot of times it's just looking at the data, evaluating mode drop and mode collapse, essentially meaning that if your data is all your images, generated images are look the same, or if all of them are from the same class. Yeah, so a lot of, I guess right now, there's the quantitative way of evaluating generative models have been debunked. There are a lot of issues with them. They're not very reliable, especially with the newer generative models, with diffusion models and transformer-based models. They don't work very well anymore because the capabilities of these models have changed and the requirement that we have from these models have changed. So right now, evaluating generative models is a very challenging topic, is a very interesting and I would say hot topic in this area. And I guess the most, even human evaluation could have a lot of challenges. Like we could spend hours talking about like evaluation of generative models, and yeah, so I'll just leave it there. Yeah, any questions about the whole presentation? I'll be happy to answer.
Is there more to this presentation, or we can start with the last round of questions?
Yeah, no, this is it. This is so. I do have some like slides for GANs, but I'll share the slides. But for this presentation, this is it.
Yeah, great. So if you can maybe send us the slides, and then we'll make it available to all our participants. So if you have any more questions for the last part, you can go ahead and ask now. And Laya and Hossein, see you guys here as well. If you have any things that you want to start with, and feel free to interact as well.
Hi, I guess I'll ask you a question. First of all, thank you so much for the nice lecture on this. Definitely learned a lot. I'm just wondering, like, what's the, like, where would the adversarial networks kind of like fit into the picture, kind of like helping out with which component of basically improving the performance of a generative model?
Right. So you could think of adversarial networks also as a latent variable model, because you again have this latent space Z that you sample from, and then you generate an example. But the way they do it is very different. The way they tackle this problem is very differently by having this discriminator and then the generator trying to fool the discriminator. Whereas here, you're using this notion of variational inference. So it's easier, I would say. The way you train the models, these two models, is very different from each other. I would say the VAEs are a lot more stable in terms of training compared to adversarial networks. But because VAEs, we assume a very simplistic prior over the data, right? For VAEs, we're assuming our data has a Gaussian distribution, essentially. like the latent space, the kind of we assume that the, how to say, the posterior, the posterior of our data, the P of z given x has a Gaussian distribution, which is of course it's a very simplistic assumption, and so this means that it won't be able to kind of learn a lot of complexities of the data, and it doesn't generate good-looking images. So I would say that VAEs are not very good for generating data examples, but they are good for essentially learning features from your data and doing inference. So one powerful tool that VAE has compared to adversarial networks is that VAEs have inference capabilities, meaning that given an input examples, you could actually kind of infer an approximate posterior over your data and kind of see what are the features of my data that are most discriminative. Whereas, so that kind of, it gives you, it has this feature reduction or like feature encoding, feature abstraction, the way you want to term it. Whereas adversarial networks don't have that. They only, it's only a generative network, a generative model.
Right, and it seems like, I mean, the main advantage of adversarial networks is that like they're really good at catching fake images, right? Like their discriminator is really good at its job for some reason, and then the adversarial networks kind of like lack on the generator, so like they have like it's very hard to train the generator. Whereas do you think if one could use the VAEs as the generators and then use a discriminator from a generative?
There are ways to kind of, so I would say there are approaches
Right.
in mixing the two.
Mm-hmm. Right.
Like we have, there's this VQ-GAN, or there is using, for example, in terms of in the generator, using the loss functions of the using the generator of the VAE, kind of to use the VAE for, or like in the VAE using the generator the other way around, actually, in the VAE using the generator of the how to say, of the, sorry, I was saying the other way around, in the, because the thing is that the KL is a very strong regularizer. Okay. Right, and it, because it, and the issue is that KL has this simplistic assumption of essentially assuming your posterior is Gaussian, right? So instead of using the KL, right, you could actually use the notions of your using the discriminator there for your KL, using, so to kind of regularize that issue, you could use it, or the other way around as well. Like, so mixing, going from the instead of the generator, in the generator of your VAE, using instead of using the kind of the mean square error, using the discriminator. Right. Using that, I've seen it a lot, because the discriminator is a very good loss function, as you were saying, compared to the mean square error. So you could use that to kind of learn more sharper images. Cool. And the other way around too. So there have been very different instances of mixing the two concepts.
Yeah, nice.
Great. Thank you for the question, Hussein, and thank you so much, Mohammed, for your detailed answer. I don't think we have more questions coming out. So if not, I just want to thank Mohammed again. I really learned a lot throughout this presentation and throughout all your detailed explanation. It's very easy to understand. So thank you so much for being one of our invited speaker again this year. Great.
Thank you for having me.
Yeah, thank you so much. I hope to see you again sometime soon. For our audience, we are having a workshop tomorrow on transfer learning in medical images and conclude the phase 1 of MCMEDx 2023, and the recording for today will be available on our YouTube channel soon. And yeah, and Mohammed, if you can share with me your slides, that would be wonderful. And I'll share with the participants.
Sure, I will do that.
Great. Thank you so much. And happy Canada Day, everyone. Have a great afternoon and weekend. All right. Bye-bye.
Bye-bye.